let's look at a couple of functions. I want to look at their relationship. F of x equals 2x plus 4. Let's go ahead and graph that. Well, we know the y-intercept is 4. 1, 2, 3, 4. Slope of 2. So that means I'm going to go up. So here's y-intercept. Up 2 over 1. Up 2 over 1. Up 2 over 1. And back the same way. Alright, now I'm going to put another line on here. We're going to look at g of x equals 1/2 x minus 2. Okay. That is a y-intercept of -2 and has a slope of up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2, and backwards down 1 over 2, down 1 over 2, and so forth. Now these two functions have a very special relationship. What I want to do is look really closely at their points. We notice that they share a point. They share the point -4, -4. This point here, -3, -2. This is -2, 0. -1, 2, 0, 4, 1, 6, and that's 2, 8. Now, if I look at the points going along g of x, this point is -2, -3. This point is 0, -2. This point is 2, -1. Here we have 4, 0. Here we have 6, 1. And here we have 8, 2. If you look at each of those points, you will notice that the x and y are switched. These functions are considered inverse functions. And that's exactly what happens. The x and y are switched. In other words, the domain and range are switched. Another very interesting thing that happens when you do a composite function here. So what I want to look at is what happens if I take f of g of x, and then what also happens when I take g of f of x. So let's do composite functions of these. Now f of x was the function that said 2 times my input plus 4. If I'm substituting in g of x, that means I'm substituting in 1/2 x minus 2. Let's see what happens when I simplify that. 2 times half of x gives me x. 2 times -2 gives me a -4. And there's a plus 4 out here. I just end up with x. If we go the other direction, g of x is the function that says 1/2 my input minus 2. Well, if I'm plugging in f of x, that means I'm going to plug in 2x plus 4 in here. Now let's see what happens when we distribute. Half of 2x is x. Half of 4 is 2. And then I have minus 2 on the outside. I end up with x back. This is called an inverse function. First thing is that they are switched, that the domain and range are switched. The second big key point is that when you do composites of inverse functions, they end up giving you x back. In other words, they give you your input that you started with back. one way to put that is that they undo each other. Now, there's another really neat thing about the graph I want to look at. If I draw in the line y equals x, which is our parent function for linear functions, look at what happens. That's the line y equals x. So another thing to note here is that inverse functions are symmetrical about the line y equals x. So they have some very interesting features. So let's look at some examples of how we can find inverse functions. Let's look at just when we have a set of points first. If I have -1, 3, 0, 2, 1, 5, 3, 3, and 4, 7. Is this original a function? If we look at our x values, none of them are repeated, so this is a function. The inverse of that is found by switching the x and y. So the inverse would be the set of points 3, -1, 2, 0, 5, 1, 3, 3, 7, 4. Is this a function? The inverse is not a function. Why? Because a 3 was paired with more than one output. The inverse is not a function. Now, remember how we could have checked to see if this was a function to begin with? We looked at the x values and see if they repeated. Well, if we want to know if the inverse was going to be a function or not, well, the shortcut is, could I have looked at the y values? Yeah, because we're going to switch them. Now, let's look at what if I had (2x plus 3y equals 6). Is the original a function? Well, yes. For each x value I input, I only get one out. The inverse of that would be 2y plus 3x equals 6. I literally switched my x and y. Is that a function? Well, for each input I put in, I still get only one output, so this one is a yes. You know, I'm going to have to put one that's not, right? Y plus x squared equals 9. Is that a function? Yes. Even though I'm squaring the x value, I still only get one y back. But let's look at the inverse. The inverse would be x plus y squared equals 9. Now, for each x value, I would get 2 y's, so this would be not a function. Now, how could I find the function or a function? Let's look at that. Now, how could I find the inverse of a function? To find the inverse of it, so let's say to find the inverse of f of x equals 2x plus 4, which was actually what we did in the warm-up. To find the inverse, temporarily, replace that f of x with y. So we end up with y equals 2x plus 4. Now, we can switch the x and y. So I get x equals 2y plus 4. And I'd like to solve for y, because if we're using function notation, we want that y, or that output, to be on the left side or by itself. So if I'm solving for y, I'm going to get x minus 4 equals 2y. Divide both sides by 2. I get 1/2 x minus 2 equals y. Now that is the inverse, but we like to use a different notation. Since this was a function notation, there is a way to represent an inverse with function notation. The inverse of f of x is denoted with this f to the negative 1 of x. What that means is the inverse of f. And we have just proved that the two functions in the warm-up were indeed inverses. Another way to verify that two things are inverses is to do that composition. So let's say I wanted to verify that, and we'll do a simple one, f of x equals x plus 2 and g of x equals x minus 2 are inverses. If I want to verify that they're inverses, the little composite function thing we did in the warm-up would be a great way to do it. So I'm going to find f of g of x, and I'm also going to find g of f of x. If they are indeed inverses, we will get x back out. So f of x is the one that says take your input and then add 2. What I'm plugging in is x minus 2. And if you'll notice, x minus 2 and then plus 2 just gives me an x. If I'm taking f of x and putting it into g, I would have parentheses minus 2. F of x was the function x plus 2. X plus 2 minus 2 just gives me an x back. So that's how you can prove that you have an inverse.